So for autonomous equations, first of all, what's the definition there? What do we mean by an equation being autonomous in the first place? Like, how do we know this equation is autonomous? Yeah, it's y prime equals a function of just y. It doesn't depend on t at all. As long as you've got, in general, y prime equals some function of just y, that essentially tells us that the rate of change in y depends only on what y is right now. It doesn't matter what t is. All that matters is if you know the y value, you can figure out how fast it's changing. And this shows up in a lot of real world examples, perhaps most notably population growth. In many, I guess, a simplified model of population growth, but a pretty accurate one, assumes that how quickly the population changes depends only on what's the population right now and whatever other factors it's being multiplied by. But that usually doesn't depend on what time it is unless you're taking into account things like seasons. But any situation where you can figure out how fast something is changing just based on how much of it there is right now. And typically what we most care about is what would be the most important value of y prime that we usually care about? Yeah, 0. Anytime y prime is 0, then if you have, that means you've found some y value that makes y prime equal to 0. And on the direction field, like for instance, what's a y value that would make this whole thing 0? What could you plug in for y that will make this whole thing turn into 0?
I'm sorry, my connection's cutting out really.
What would you, or what could you plug into y? Yeah, 3 or 7 or 0 will make this whole thing turn into 0.
Would it be plus or minus 3 because it's squared?
Well, if you plug in -3, you get -3 minus 3, which is -6, which doesn't turn into 0 when you square it. So it's the y minus 3 in parentheses, and then that result squared, which is not the same as y squared minus 3. If it was y squared minus 3, then yeah, 3 or -3 would work. But y minus 3 would only be 0 if y is positive 3. So that means if we were to draw out a direction field of t versus y, the usual direction field would have equilibrium at 7, because if y is 7, then no matter what t is, the slope is going to be 0. And if y is 3, then the slope is going to be 0 regardless of t. And if y is 0, then the slope is 0 regardless of t. So we can see the equilibrium solutions from just figuring out what y values will make the whole thing become 0. To figure out what type of equilibrium, though, and the overall behavior, we need to know what's happening in between. And one of the big important properties of an autonomous equation, let's say we plug in some other value, maybe, let's say 5. If you plug in 5 for y, we get 5 times 2 squared is 4, times 2 again would be 40. And the negatives, I think, cancel out. So at that point, the slope would be 40. It would be very steep at that point. But let's say we move to the right. Let's say instead of having t equals 0, y equals 5, let's say we had t equals 3, y equals 5. Now what would the slope be? If we keep the same y value, but just change the t value.
It's the same, right?
Yeah, it's going to be the same slope. No matter what t is, if we have a certain y value, that y value alone determines the slope. That's what it means to be autonomous. And ultimately, for purposes of drawing a direction field, that means we don't need to care about t. Instead of looking at all locations on the direction field, we can just take any one cross-section, map out that column of the direction field, and then any other column is going to look identical. So that column, we usually call the phase line, is often useful to draw that separately. So instead of drawing out the whole direction field, let's just draw out that one cross-section. The phase line is looking at the various y values and which ones lead to equilibrium and what type. And it is really just a cross-section, a vertical cross-section of the direction field. So we already know that 0, 3, and 7 lead to equilibrium. So let's mark those on the phase line. We know those all count as equilibrium. And we could just start plugging in numbers in between, like plug in 5, we found we got positive 40, so we know it's an increasing function in that zone. But it's often useful to, as you said earlier, to graph out this function first to get an idea of where it's going to be positive and where it's going to be negative. The graphing out the function usually isn't necessary, but it is often a useful first step to get an idea of the shape of the values we're dealing with. So if we start by graphing that out, in this case, putting y on the horizontal axis, we make it both positive and negative, actually. So instead of having our usual t versus y axes, like on the direction field or the actual solutions, we're instead going to graph y as an independent variable and f of y, this whole thing, as the dependent variable, the function itself. So in this case, f of y is all this stuff, negative y times y minus 3 squared times y minus 7. And to draw the graph of that, first of all, if we multiply this out, we're going to get a polynomial. And that polynomial has what degree? What's the highest power going to be? Yeah, if we multiply this out, this y minus 3 squared is going to give us a y squared and some other stuff. Times y makes it y cubed, times this y is going to make it y to the 4th. So we're going to have a y to the 4th and a bunch of other stuff, presumably a y cubed term, a y squared term, a y term, and a constant term. But the y to the 4th really determines the main idea of the shape of the graph. A quartic function, 4th degree, is going to look like sort of a W shape. And it could be an upwards opening W or a downwards opening, sort of more of an M. And what's going to determine which one of these it actually is? Yeah, the sign on that y to the 4th. And if we multiply this out, the y squared is going to be positive times y is still positive times negative y. That gives us a negative y to the 4th. Negative y to the 4th suggests we've got this downwards opening, sort of an M shape. So we should expect this general shape for our y versus f of y graph. And what do we know about the intercepts? Where is it going to hit the axis?
Three, 7, and 0.
Yeah, so we can mark those right away. 0, 3, and 7. And since we know this negative sign suggests a downwards opening shape, we know that from 0 to the left, it's going to be going downwards. From 7 to the right, it's going to be going downwards. In the in-between zone, the 3 here comes from the y minus 3, and that's being squared. So that suggests what should it look like near that point? If you ignore everything else,
Positive.
what's happening to that?
It was positive.
It is going to be positive because if you, well, that alone is going to be positive. We should probably look at the other pieces also. If you look at those in-between zones from 0 to 3, this is always going to be positive, right? The y minus 3 squared. This piece is always positive. If we're between 0 and 3, actually between 0 and 3 or between 3 and 7, is y going to be positive or negative? If we're to the right of 0, y is going to be positive, right? So in this region, y is positive, and we haven't gotten to 7 yet. So if y is a number less than 7, is y minus 7 going to be positive or negative? Yeah, should be negative. So we've got negative, positive, positive, negative. That works out to a positive. So in this entire region, from 0 to 3 and from 3 to 7, we should expect positive values. We can also see that from the fact that if you ignore everything else, y minus 3 is being squared. So near that intercept, it should act like a parabola. So near that intercept, we should expect it to act kind of like a parabola, hitting the axis and bouncing off, but not going through. As opposed to if you were just graphing negative y or something y, it's going to go through the axis. So as 0 goes through the axis, ignoring everything except the y minus 7 is going to act like a linear function near that point. So it's just going to go through. But near 3, y minus 3 squared means it's going to act more like a parabola. So it's going to look something like this. We haven't done any calculations to see how high or how low it goes, but we've at least gotten all of the zeros, 0, 3, and 7, all of the roots of the function. And we have an idea of which intervals make the result positive versus negative. And that's really what we most care about. And you can do that by plugging in values in between, like plug in 5 for y, check if it's positive or negative. Plug in maybe 2 for y, check if it's positive or negative. And maybe plug in 10 or 100 or 1,000,000 for y and check if the result is positive or negative. But if you know a little bit about graphing polynomials, that can make it much faster, especially if it's already factored, because then you can immediately see where it's going to hit 0. Any questions on that graph so far? So at this point, we can now take the y-axis, and we're basically taking that y-axis and turning it upright to make the phase line. This y-axis essentially is the phase line. We've got 0, 3, and 7 as the important equilibrium values, because that's where f of y, which represents the slope, is 0. In the in-between regions, what do we know, for instance, about the region between 0 and 3? In that region, what's the sign of f of y?
Positive.
Right. And if f of y is positive, that means y prime is positive, and therefore the function is an increasing function. So if the y value is between 0 and 3, we know we've got an increasing function, because in that interval, the derivative must be positive. Likewise, from 3 to 7. In all those y values, the f of y, that is y prime, is positive. So in this interval, if y is between 3 and 7, we also have to have an increasing function. What about if y is greater than 7? If we have y values greater than 7, what do we know about f of y?
Decreasing.
Right. Well, not so much that f of y is decreasing, but that f of y is negative, which means y itself must be a decreasing function. It doesn't really matter whether f of y itself is increasing or decreasing. All that matters for f of y is it positive or negative or 0? In this interval, f of y is a negative value, which means y has to have a negative derivative. It's going to be a decreasing function. And likewise, if y value is less than 0, we know f of y is negative. So that also means y is a decreasing function, has a negative derivative. So by putting these arrows on the phase line, these arrows represent, is that function increasing or decreasing? Is y itself increasing or decreasing in those intervals? So we can say that for any y values between 3 and 7, that has to represent an increasing function, for example. Any questions on that phase line so far? And we can now use that to analyze or categorize the equilibrium solutions. For instance, we know y equals 7 is equilibrium. If you start at y equals 7, you'll stay there forever. But what happens if you're just near y equals 7? Like if you're a little bit above or a little bit below, what's going to happen?
It converges on 7.
Yeah, all these values nearby converge on 7 because everything's being pushed towards 7 from both directions. So what kind of equilibrium is that?
Stable.
Yeah, that is stable equilibrium. Whereas what would be unstable equilibrium here?
0.
Yeah, if you're at 0, you stay there forever, so it's equilibrium. But if you're a little bit off, like a little bit above, you get pushed further above. If you're a little bit below, you get pushed further below. So everything nearby is getting pushed away from equilibrium. So we call that unstable. And note that those correspond to a point that's passing through the axis on the way up. That's the unstable equilibrium, versus a point passing through the axis on the way down. That's stable equilibrium. Because of how we're changing from negative value of y prime to positive, or positive value of y prime to negative. But if you have trouble remembering that, which I usually do, I don't really like the memorizing rules approach, you can always draw out the phase line and check the arrows on that. I find that's usually the most direct way of checking what kind of equilibrium you've got. Also at 3, what's going on? If you're at 3, you stay there forever, but what if you're near 3?
It's semi-stable.
Yeah, we call this semi-stable, because if you're a little bit above, it acts unstable, you get pushed away. But if you're a little bit below, it acts like it's stable, you get pushed towards. So stable on one side, unstable on the other. We call that semi-stable, or sometimes it's called half stable. So that would be the phase line. It tells us, just based on these arrows, what type of equilibrium we're looking at. Any questions on that so far? And then from the phase line, we can draw out the direction field much more easily. We've already marked the equilibrium values. We can also now put in at least roughly sketch out the in-between regions. We know between 0 and 3, we've got positive slope, presumably kind of weak when we're near equilibrium and then steeper if we're in between. Likewise, between 3 and 7, positive slope, weak if you're near equilibrium, steeper in between. And we already found its slope 40 at 5, so that's going to be really steep. If we're above 7, we've got a negative slope, and presumably getting more and more negative as we get further up. And likewise, below 0, we've got a negative slope. So the phase line tells us information about one typical column of the direction field. But of course, any column is going to look identical to that because t doesn't matter. So we can copy down the exact same slopes further down the line in the t direction. So it's going to look something like this. So once you've drawn out the phase line, you can sketch the direction field really quickly, and then even draw in some sample curves. Like for instance, if you start a little bit above 3, you're increasing, then a little bit faster, but then leveling off towards another asymptote. Or if you start below 0, that looks like just something like exponential decay or exponential growth towards negative infinity. Or up here, exponential decay converging on 7. Any other questions on that approach? Yeah. So this is generally a very useful overall method for quickly and more geometrically analyzing any autonomous equation. As long as it's y prime equals something about y alone, then this approach works really well. Especially if it's something that you can't solve or that would be too tedious to solve analytically. But as long as you can graph this function, whether by hand or on a graphing calculator or computer graphing software, you can then turn that graph of y versus f of y into a phase line, figuring out where's equilibrium and in between, is it increasing or decreasing, and then categorize equilibria as stable, unstable, or semi-stable. Then from that phase line, copy, paste, 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 paste to get all the columns of the direction field. And then you can start sketching in sample solution curves. Yeah, go ahead.
My question was just like for the first part, because he said we can't use calculators. Mm-hmm. So like if we were tossed like a really weird function, I won't be able to sit there and do the math, mm-hmm. Or whatever. So that's really what my question was, is how to just know what that initial phase plane graph looks like without
the f of y graph.
That guy.
The y versus f of y graph, we don't really need a whole lot of detail on that. All we really care about for purposes of constructing the phase line is where is that graph going to hit zero? Where does it hit the axis? Right. And also in the in-between regions, is it positive or negative?
Right. So I can just really focus on knowing the signs, not actual values.
Yeah, exactly.
Okay.
So even if it's a graph where you don't really know in advance what its shape is, as long as you can identify all the y values that would lead to the result being zero, that tells you all the intercepts you care about. And then even if you don't know what the shape is going to be, you can just check any one sample value in between. Like if we know it's 0 at 3 and 0 at 7, we could just throw in any number we want, maybe plug in 4 for y and check, is it positive or negative? Again, you don't even need to know the value. You just check, is this going to lead, if we plug in 4, would each of these pieces lead to a positive or negative result? And anything where you've got like a term or a binomial or whatever to an even power, that's always going to be positive. So that makes it even easier to work with. And anytime it's in factored form, polynomial, that's extremely useful because you can immediately see that the factors lead to specific roots. And then you just check the in-between values. Any other questions on that? Then let's see what we would do differently if we don't have specific numbers, if some of the parameters are listed as unknown constants. And see if we can try the same approach. Let's say our equation is like that one in the textbook, y prime equals ay plus b. Or I guess ay plus by squared, it says here. And it also specifies that a and b are both positive numbers. And it also mentions y naught is greater than or equal to 0, which really just means we're not considering initial conditions below 0. We can focus on our direction field just being the first quadrant. We don't have to worry about y values less than 0. And usually we don't care about t values less than 0 anyway, partly because t equals 0 typically represents the beginning of the experiment. And also t doesn't matter because this is an autonomous equation anyway. So we're ignoring any y values less than 0, and we're assuming these are unknown constants that are both positive. So let's see what we can do here. Even without knowing what a and b are, other than that there's some unknown positive values, if we were to try graphing y versus f of y, that is ay plus by squared. Again, we'd want to start by figuring out, are there any y values that lead to the whole thing being 0? And since this is a polynomial, I think it would be a good idea to factor it first. What can we factor out of this? Yeah, we can factor out y. We're left with a plus by. So where is this going to hit 0? What y values will make this 0? Yeah, y prime is 0 when y is 0 or negative a over b. So we can mark those on the graph. 0, and we don't know what a and b are going to be, but we at least know they're both positive constants. So negative a over b is going to be some negative value, which kind of suggests we're going to disregard it. But I'm going to mark it on the graph for now anyway, just for the sake of completeness. So negative a over b is going to be one of the locations, one of the y values where we hit 0. And then 0 is going to be the other one. And then if we wanted to check some in-between values, first of all, we could examine this more geometrically. If we're graphing ay plus by squared, what shape would you expect that to be on the graph? Yeah, it's going to be a parabola. And would you expect upwards opening or downwards opening? What would determine that? Yeah, because that's always determined by the sign of the coefficient on the highest exponent, y to the highest power. We know that b is positive based on this criteria here. So that means it's going to be an upwards opening parabola. So we should expect it to look like this. But even if you don't recognize that right away, you can still try filling in some values. Like if we fill in, and again, we don't even know what a and b are, but if we try filling in a positive value for y, note that this is always going to be positive. Or actually, we should probably look at factored form. If we're looking at a positive value for y is positive. Positive plus positive times positive is going to also be positive. So the result is positive. So we've got positive values for f of y if y is positive. In between, it can kind of be difficult to tell, but let's say we're looking at the extreme. Let's say we're plugging in an extremely negative number. This is going to be negative. No matter what a and b are, if y is negative enough, this is also going to be negative. Negative times negative is going to lead to positive. And then in between, if y is negative, but only a little bit negative, y is negative, but a, let's say a is really big, plus a little bit negative is still going to be positive overall. So negative times positive results in negative f of y values in this region. So that would be our rough sketch of a y versus f of y graph. Any questions on that so far? Now that we've got that graph, let's see if we can draw the phase line that matches it. What important y values do we want to mark on this? Yeah, y equals 0 and y equals negative a over b. Those are the points where the y values that make f of y equal to 0. And then for the in-between regions, or these three intervals that we've split it up into, we know for y values that are greater than 0, f of y is positive, which means y prime is positive. So in this region, is it an increasing or decreasing function? Yeah, should be an increasing function because we know in this zone, f of y is positive. In fact, you might find it useful to just map it out on the y-axis. If you just think of this as a bar that can be marked positive or negative. In this zone, f of y is positive. In this zone, f of y is negative. And in this zone, f of y is positive again. So we're splitting this up into a positive region with y values that are very negative, a negative region when y values are just a little bit negative, and a positive region when y values are positive. Yeah, I think that is a good way to draw it, to sketch out this bar and just mark off which regions are positive versus negative. And then again, you could think of this as taking that bar and turning it upright to make the phase line. Any region where f of y is positive, that means y prime is positive, so you've got an increasing function. Any interval where f of y is negative, that means y prime is negative, so you've got a decreasing function in that zone. And then here, once again, we've got positive values of y prime, so that represents an increasing function in this zone. And now we can see from this phase line, what type of equilibrium are we dealing with? How would you describe these equilibrium values? Yeah, we've got an unstable equilibrium at y equals 0 and stable equilibrium at y equals negative a over b. And then we could use that to draw out a direction field. With 0 slope at 0 and negative a over b. Positive slope if we're above y equals 0. Presumably starting off just a little bit positive and then getting steeper and steeper as we get further from equilibrium. Also positive below negative a over b in the same sort of way. And then negative slopes in the in-between zone. Again, presumably fairly flat if we're near equilibrium, and then getting steeper if we're further from equilibrium. So there's our direction field. And now if we want, we can even draw in some sample solutions, some integral curves, following the direction field lines as closely as possible. So it looks like these are the sorts of end behaviors we should expect. Any negative initial conditions will converge towards negative a over b. Any positive initial conditions will diverge to positive infinity. But also this problem specifies that we're only looking at positive initial conditions anyway. So I would just say all of those initial conditions lead to diverging to infinity, positive infinity. Except of course, if you start at 0, in which case you'll just stay at 0, since that's equilibrium. Any other questions on that? So generally, you can analyze this sort of thing, even if the differential equation has some unknown parameters in it, as long as you at least have some information about whether those are positive or negative. Bifurcation diagram. The bifurcation diagram, yeah, the bifurcation diagram is really analyzing what happens if you change those parameters. Like let's say, and usually we look at just one parameter changing. So let's say, for instance, what would work well here? Let's say we know the value of b, but we're allowing a to change. So let's say b is 5, but a could be anything, positive or negative. Since a could be anything, we can't really analyze this in the same sort of way we did before. Previously, we at least knew a and b were both positive numbers. But this can lead to some issues here, because if we factor this, we get, does that work? Actually, let me change that. Let's say, we have 5y minus ay squared, or plus ay squared. In that case, when we factor that, what would it look like? Yeah, y times 5 plus ay. And so the actual shape we get is going to vary depending on whether a, or what sort of value a is. Since a could be any real number, we should expect this to be, if we graph f of y again, we should still expect this to be a parabola. But the problem is we're going to get different parabolas depending on what the value of a is. And we can't even just sketch one typical one because a has some variability here. A could be what sorts of numbers? Yeah, it could be positive or negative. Could even be 0. If a is positive, because note that we're always going to get 0 as an intercept. The other intercept, if you said this equal to 0 and solve for y, what would you get? Yeah, negative 5 over a. And that could be a positive number or could be a negative number, depending on the value of a. So you might have negative 5 over a being positive, and you get a graph like, actually that would require a to be a negative value, right? If a is negative, what would that tell you about the parabola? Yeah, it would be downwards opening. Or alternatively, maybe A is a negative value. Or sorry, maybe A is a positive value, which means -5 over A would be a negative value. But then that positive value for A would mean it's an upwards opening parabola. So you could have either one of these parabolas, and those are going to lead to very different sorts of shapes of the direction field, very different phase lines. In fact, you could even have A being 0. If A is 0, what happens with this? Yeah, this second intercept is undefined. You end up with division by 0. But if we go back to the original equation, if A is 0, now what's the only y value that leads to y prime being 0? Yeah, 0 is going to be the only intercept. And if we graph 5y, that's just going to be a straight line through the origin. So it looks like there's really 3 possibilities here. Depending on whether A is positive, negative, or 0, we might get an upwards opening parabola on the left side, or a downwards opening parabola on the right side, or even a straight line through the origin if A happens to be 0. So f of y gets a variety of different possibilities. We can analyze those with this idea of a bifurcation diagram, though. A bifurcation diagram is essentially looking at all the possible ways A could influence the phase line. So what we're going to do, if we take a look at the y values again, the equilibrium values. Where is equilibrium? We get equilibrium at, no matter what A is, y equals 0 is always going to be equilibrium. And our other equilibrium depends on A. We ended up with y equilibrium equals -5 over A. So what we can do is we can make a graph showing how A influences the equilibrium solutions. That's really all a bifurcation diagram is. A bifurcation diagram describes how the equilibrium solution or solutions are related to the value of that unknown parameter. So instead of graphing t versus y or y versus f of y, we're going to make a graph of the possible A values versus the resulting equilibrium values. And we're going to have to make two paths on this graph. One of them showing that the equilibrium value is always going to include 0. So no matter what equilibrium, or no matter what A is, you can always have y equilibrium equals 0. What would the graph of y equals 0 look like? If you just graph y equals 0, yeah, that's just going to be a flat line. So 0 is always equilibrium, no matter what the value of A is. But also the equilibrium values could include -5 over A. If you graph A versus Y and the curve you're graphing is y equals -5 over A, what sort of shape would that look like? What would you get if you just graphed like y equals x or y equals 1 over x? It's not going to be a line because it's not -5 times A, it's -5 divided by A. You remember what the graph of y equals 1 over x looks like? This 2-part hyperbola curve. Because if x gets larger and larger and larger, 1 over x gets closer and closer to 0. But the negative is going to make it flipped over. So we're going to have a curve like this and a curve like this, approaching the axes as asymptotes. So these would be the graph of the y equals -5 over A. And if you look at the in-between values, since we're talking about, like, let's say you choose a value for A. If we just choose some A value, the cross section of this is now a phase line. We choose an A value and we now have 0 is one of the equilibrium values, -5 over A is the other equilibrium value. And if we take a look at the in-between values, let's say y is positive. This is reflecting when a is a positive value and y is a positive value. So 5 times a positive plus a positive times a positive, that's going to be positive. So this entire zone is going to be an increasing function. Or if we plug in a big negative for y, this will be negative, but y squared will be positive and even more positive. So this zone is going to be positive, an increasing function. And then in between, we're going to get a decreasing function. And you could even choose some specific numerical values to try this out. Plug in an in-between value, and this is going to give you a negative result. So a single cross-section of the bifurcation diagram is a phase line for that specific a value. Or if you chose another a value, this is still going to be an increasing function, decreasing function in between, increasing function. And likewise here. So any single cross-section of this bifurcation diagram is a phase line. If we take a look at the 0 point though, because there's kind of a discontinuity here, if we're talking about a equals 0, there's only one equilibrium. And in that case, if y is positive, does y prime become positive or negative? Yeah, positive. And that kind of matches the continuous, all of these are positive. And if we're below, if y is negative, then y prime is also going to be negative. If we continue over to this side, no matter what a is, as long as y is negative, this whole thing is negative, and a we're assuming is also negative, so we get negative values over here. If y is very large, then this term dominates, and we're assuming a is negative, so we get negative values here as well. But in the in-between values, if y is positive, but not all that big, this term dominates. So you get a positive slope in the in-between values. And it looks like it's going to continue this pattern throughout the whole thing. And you can always check some specific numbers to verify, like actually plug in some numbers for a and check the in-between values. But it looks like this is what our bifurcation diagram is going to look like. These blue curves represent the y equilibrium solutions at certain a values. And these arrows in between represent in between those equilibria, should we expect increasing or decreasing functions. And again, you can choose any particular a value and take that vertical cross section, and there's the phase line that corresponds to that particular a value. So we've got equilibrium at 0 and some positive value, specifically -5 over a. And it looks like -5 over a will be stable equilibrium, and y equals 0 will be unstable. Likewise, over here, we've got some 0 value, which is unstable, and some negative value, which is stable. Any questions on that? All right, so give that a try with some other examples. You can basically just make up any first order autonomous equation. Y prime equals something about y, and optionally including an unknown parameter a, and follow this same approach. If there has an unknown parameter in it, you can draw out the bifurcation diagram and figure out how the equilibrium values and the type of equilibrium depend on the value of a. And again, any vertical cross-section of the bifurcation diagram is a phase line for that a value. So give that a try. Let me know if you have any other questions, and I will see you next time. You're welcome.